Hello and welcome to this video on polarization. So we're going to look at what is polarization, how do we polarize certain waves, and why does it all work. So the first thing I want to do is show you a short clip of polarization in action, and then we're going to spend the rest of this video trying to explain what exactly we've just seen. So you can see that this is a filter being held in front of a regular laptop screen, and you can see that when I rotate the filter, it blocks out all of the light from passing through, and when I rotate it back, the light comes through again. Okay, so why is this happening? We first have to look at the idea of what is the composition of light. Okay, and light, we know, is an electromagnetic wave. But what does that mean? Okay, so electromagnetic wave means that we have both an electric and a magnetic field. Now you'll come to learn in A2 fields and their consequences about this idea, but the general tip is that we can never have an electric field and a magnetic field acting in the same direction. They always have to be perpendicular to each other. So what's actually happening with an electromagnetic wave is if I just set up some axes, you're going to have to imagine these being three-dimensional. So this is coming almost out of the screen. I could draw that one a little bit more like this. Let me use a different color to represent the electric field, and then I'll use a different color to represent the magnetic field. But the electric field, I'm going to say, is going to oscillate vertically. Now I'm not the best artist, so I'm going to try my best to get this so that it looks like it makes sense. Okay, so let's just have this. This is our electric field. Okay, now let's choose a different color for the magnetic field. This is along the this electric field goes along this axis, this vertical axis. The magnetic field is then going to be 90 degrees to this, so it's going to go across this axis, and it's going to look something like this. Okay, so like I say, I'm not the best at drawing, but this is the magnetic field. Hopefully you can see what this is meant to look like. Maybe if I take the red pen and sketch it in a bit, it'll make it a little bit more obvious. So this is vertical, this is what we can see, and then we get the blue pen, and this is just behind it. Okay, but this comes over the top and this is behind. Okay, so hopefully that makes it a little bit clearer what's actually going on. Okay, so this is the general setup of any light ray. So when you hear about the electromagnetic spectrum, all of those waves have this exact structure. And what that means is that they're not only oscillating as a transverse wave in one plane. So what I mean by a plane is the X plane, the Y plane, or the Z plane. I should probably do that one over here actually. So they would be planes, so either vertical, horizontal, or going into the page or coming out of the page. And they actually do two at the same time. So what I'm going to refer to this as, instead of writing it as just instead of having to draw this out every time as an electromagnetic wave, I'm just going to refer to it with this kind of diagram here. So this vertical line is the electric field that goes vertically, and the horizontal line is the magnetic field. But I could rotate this and make it look like this, because it wouldn't change the fact that it's still a light wave. I could then rotate it even more and keep going around, so it doesn't really matter which one is the electric and magnetic field. But what we can do is say that if we're going to send out a bunch of light into something, then it's oscillating in all planes. Okay, so light generally oscillates in all planes. Okay, even the diagonals. So we have kind of this 360 rotation that we could have light rays in. the idea of polarization is we want to limit the amount of planes that this light can oscillate in to just one plane. Okay, so the way we do that is by using that device called a polarizing filter. Okay, so the way polarizing filters are designed is that they're kind of like almost like prison bars is the way I've always imagined it. So a polarizing filter, I'm just going to use a rectangular one rather than a circular one. They're aligned so that they only let a certain plane of light through. So this, let's say this one is vertically aligned. It has, you can think of it as just having miniature bars across it. So if we have some sort of light ray that's going to come through and it travels through here, we're only going to get the vertical that can actually pass through, because all of the horizontal ones are going to get blocked by these bars. So are the angular ones, and the only light that can actually pass through is vertical. And the light we get on this side is now what we call plane polarized, because it only oscillates in that individual plane. Now the interesting thing with this is that we can do this again and have a second polarizing filter, which is what a lot of exam questions are going to ask you. And if we put a second polarizing filter and we have this, let's make it a different alignment, so let's make it horizontal. This is aligned horizontally. It means that no light actually comes out on the other end. We don't get any oscillations because that vertical light is going to get blocked by those bars. So this actually completely cancels out any light that was originally emitted just by using two polarizing filters. Now a very common exam question is to say, what's going to happen if I rotate this around 360 degrees? What would I see? Well, if it's like this, what we'd usually do is draw an intensity profile for this. So I'm going to draw it down here. So this is going to be a graph of the intensity, so basically how much light are we detecting here against the angle that we're going around. So let's say we start, let's actually start vertically, so we can start with some. So let's say we start with having a vertical bars. That means light can pass through. Okay, so we will still see light, so we'll get high intensity through here. As we start to rotate this, if we rotate it through 90 degrees, it then becomes horizontal. And when it's horizontal, we then can't have any light pass through, so our intensity falls to 0. Okay, if I continue to rotate it, so I get to 180 degrees, that 180 degrees is going to take it back to being vertical. So it's going to go back to being vertically aligned, which means that we're going to get light out again. We're going to see this light, so it goes back up to being a maximum, and then you can probably guess if I rotate it by another 90 to get to 270, it's going to go down to a minimum, and then the last 90 to get back up to 360 degrees, you get back to your original position, you've got this kind of intensity profile. So this is 360 degrees over here. This is a very common exam question on polarization. They'll usually tell you to either draw this graph to show how the intensity changes, or they'll tell you to describe it with words, in which you just basically describe that as soon as you rotate through 90 degrees, you get to a minimum. When it gets to 180 degrees, you're realigned in the vertical position, so you get a maximum, then a minimum, then a maximum again. Okay. From here, we can just look at the uses of these things. So this is kind of the experiment that has told us that things are polarized. And the uses of these things are going to be partially based on this idea that if we rotate this, we can change the intensity that's coming through. Okay, so the first use is the one that I've already showed you, which is camera lenses. Okay, so the device that I was using in that video is what we call a CPL lens. So a colored polarized light lens. Sorry, circular polarized light lens. The idea of it is that to reduce glare. Okay, so in general, it just reduces glare from a surface. Now, the reason it has to do this is because if we have light from the sun is unpolarized. Okay, so let me just make a little bit of a barrier here. So light from the sun is going to come into the atmosphere completely unpolarized. Say you're trying to take a picture of a lake or something like that. This light is then going to hit the surface of the lake, and reflection can also cause something to be polarized. Okay, so if something gets reflected off this, then it then becomes polarized in the direction or in the plane of that surface. So if the surface is horizontal, we have polarized light in that plane, which means that you're going to get basically the glare from the surface, and you can remove that by putting a or in this case it's circular, so a circular polarization filter which has these bars which stops that glare. So you can just get the original amount of light and you don't have any glare from this, and it makes the images just a little bit more crystal clear. The second use that we can look at is ski goggles. So ski goggles work in the exact same way. When light comes down and reflects off the snow plane polarizes it, and if you're skiing, you kind of don't want glare, because then if that like hurts your eyes, you close your eyes and you're skiing at high speeds, it's very dangerous. So this also reduces the glare from the snow, like from the light that's been reflected off the snow. The last use is radio antennas. Okay, so these radio waves, when they're emitted from like a radio station that you'd have to pick up in order to tune into like a radio station, the waves that are emitted by the station are originally plane polarized, which means that if we have the antenna aligned in the wrong plane, we're not actually going to detect any signal, so we won't get to hear the radio show or anything like that. So the light that's emitted might be vertically polarized, in which case your antenna must also be in the plane, in the vertical plane, so that it can detect that signal. So radio waves are plane polarized. So the detector or your antenna must be aligned in the same plane. Okay, this is why you can get a better signal just by rotating your antenna slightly, just to make sure you're completely aligned rather than only partially aligned. Because what you can tell about being partially aligned is at this point, if you were to go just to 45 degrees, you're only blocking out half of the light, which means that if you're going to go halfway, you're only going to get half of the signal. Okay. So this is everything you need to know for A-level polarization. The extra thing that was in this video that we haven't mentioned yet is the fact that most light from computer screens is already plane polarized. So polarization filters are actually pretty cheap. So if you really wanted to, you could go and get one and then just test it. Your school will probably already have a polarization filter. So if you go and ask your teacher for a polarization filter and then just test it on a laptop screen or a computer screen, you'll tend to find that most things will be plane polarized, and then you'll get that effect that we saw in the video. Okay, so this is polarization. Thank you for watching.